Recording in progress.
Good morning, everyone. Can you hear me?
Так, чуємо.
Так.
Вітаю.
Thank you very much. I ask you to mute your microphones and let me start our webinar. Welcome you to today's webinar on small modular reactors. It's absolutely pleasure to have you all on today's webinar, and let me introduce myself. My name is Sergey Pugac. I'm head of Technology Transfer Office of the National Science Center Kharkiv Institute of Physics and Technology, National Academy of Sciences of Ukraine. And I am coordinator of NURECAB project and national contact point in the fusion area. So before we start our meeting, I would like to notice some technical issues. First of all, we have a very short agenda today, only 2 presentations. One of these from my side about NURECAB project, and the main presentation from our colleague from Italy, Professor Marco Ricotti. It's a very pleasure to have you today. And the language of our meeting is English, and I'd like to ask you to you have an opportunity to ask questions in our chat. Please type your question in the chat, and you can ask by raising a hand as well. But I would like to ask you to do this after all of our presentations. The topic of our webinar is small modular reactors, and as all we know, the energy topic, energy production, is at the heart of global challenges today. And SMR represents one of the most promising innovation in nuclear energy. It is a scalable, small reactors that have potential to modify the way how to generate nuclear energy as a clean, reliable source addressing to the security and safety issues as well as environmental concern. And I would like to say that I have a friend from Belgium. It's Katerina Pilugina, who is our consortium member and the program manager of European Nuclear Education Network. And I would like to give some words to Katerina to say greetings and to introduce our main speaker today, Marco Ricotti. Katerina, please.
Good morning, everyone. Can you hear me well?
Yes.
Okay, good. Yes, I'm happy that we can, at the end of the year, Marco honored us by his presentation, because he is very good and experienced expert, very known in Europe. And we are really happy that you have time for us, and you can share your information about the the small modular reactors and how it goes in Europe. So a few words about Marco Ricotti. Marco Ricotti is a full professor of nuclear plants in Politecnico di Milano, Italy. He is a PhD in nuclear engineering, and his research activities are mostly related to small modular reactors and advanced modular reactors, which includes also research on solutions for space applications. He has a rather a big list of different, let's say, awards and different involvements, and I'm happy to share this with you as well. So he is you know all of you know about European Small Modular Reactors Industrial Alliance, which started its was established in the beginning of this year, and Marco is the technical working group leader on skills, which is actually very important for us and for a NURECAB project as well, to be in touch with this kind of expert, this level of expert. He is also a member of steering committee of ESARDA, which is European Safeguards Research and Development Association. He is a director of specializing master on nuclear safeguards, which is being led by European Nuclear Education Network, and Marco is a director of this master program from the Politecnico di Milano side. And at the same time, there is a big association of Italian universities on nuclear technology, working in nuclear technology, and Marco is the president of this association called CIRTEN. At the same time, he had a big involvement in during his life, working life, and professional experience in different types of activities, and at the same time at the industry, where he was involved in decommissioning and red waste management organization. He was a president of Sojin, which is a state company dealing with decommissioning and red waste. So, and also he is, of course, involved in the activities of European Nuclear Society, and he is one of the drivers of, I would say, from my side, he is one of the drivers of nuclear in Europe, and one of the main drivers of nuclear coming back to nuclear in Italy. So actually, if you heard about some news related to Italy's coming back to nuclear, is Marco did a lot to make it happen. So he is really very active in promoting nuclear in Europe and in Italy. So this is a not very short, but introduction of Marco, but I wanted everybody to understand how what an expert is now in front of us. And I would give a floor back to Sergey to say a few words about our project, just to make sure that everybody understands what we are doing. Please, Sergey.
Thank you very much. I try to share my presentation, and can you see it in full screen?
Yes.
Okay, thank you. We arranged this webinar within the NURECAB project that related to nuclear research and education capacity building between Ukraine and European Union. It is a 24 months project that started in September the 1st this year. That it includes 9 participants from Ukraine and Belgium. There are 2 main objectives of our project: support and improvement of nuclear education and training programs in Ukraine. And we have some sub-goals for these objectives: quality improvement of nuclear education and training program in Ukraine, reducing the gap between nuclear education and training program of Ukraine and nuclear sector needs, attracting young people to nuclear research and engineering. And the second one objective is strengthening integration of Ukrainian research and education entities and their infrastructures into the Euratom Research and Training Program. And sub-goals for this objective are strengthening cooperation between UR and EU research entities and academia to improve the participation of their researchers in the Euratom program, enhancing Euratom NCP competencies and communication tools, and raising awareness about Euratom program among Ukrainian stakeholders. There are 9 participants in this consortium, and we have 5 universities from Ukraine, from Kharkiv, from Odessa, and Kyiv that related to nuclear education, and there are 3 affiliated entities: European Nuclear Education Network, it's Ukrainian Nuclear Society, and the company National Nuclear Energy Generating Company Energoatom, and project coordinated by National Science Center Kharkiv Institute of Physics and Technology. There are 6 work packages in this in our project. The first one related to nuclear education enhancement, identifying gaps and strengthening pathways. It's about studying of the gaps between education and industry, research analysts, and providing some additional courses for universities in the nuclear area, fusion and fission. And the second work package is about staff training for Euratom program stakeholders. First of all, it concerns training for teaching and research staff at universities and improving skills of national contact point in Ukraine. The third work package related to strengthening national and international cooperation. It is about arrangement of webinars, workshops, and supporting of travels for our researchers related to universities, research centers, as well as industrial companies. The first work package is about young generation, nuclear young generation in Ukraine. It's about attracting young people to our sector, to our universities, to our research institutes and industrial companies of nuclear sectors in Ukraine. And the fifth work package is about communication, dissemination, exploitation. It's about sharing our results among the broad audience and among our colleagues in Ukraine and abroad. And work package 6 is about efficiency of implementation of our projects, project management and coordination. I would like to present some expected results and performance instead of a presentation of our work packages one by one. So we provide the study of knowledge gaps between existing education programs and needs of nuclear sector in Ukraine. And we do this right now. And thank you very much for all our experts and researchers who are involved in this. After that, we are going to create some recommendations for quality improvement of nuclear education courses and training program in Ukraine. We are going to create 10 improved or developed new courses in fission and fusion areas. And we are going to integrate Euratom corporate learning system to 5 UR nuclear universities, provide 4 trainings for universities teaching and research staff. We are going to provide 65 participations for Ukrainian stakeholders to take part in Euratom events, workshops, seminars, and other nuclear European events during the next 2 years within the implementation of our project. And we are going to provide 4 NURECAB workshops, 3 UA meetings, and we're going to arrange Euratom Info Day in 2026 when the next work program will be announced. As well, we provide annually our NCP workshop. All of this activity will be done to create recommendation for integration of Ukrainian nuclear research and education community into Euratom program. As well, we are going to arrange for trainings to Ukrainian audience on different issues of Euratom and Horizon Europe program. One of the key activities of our project is directed to nuclear young generation. We are going to arrange 12 events for this audience, 15 universities activities for young generation to attract young people from school to the schools of physics and technology related to nuclear education in Ukraine, and provide 12 travels for PhD students, create recommendations for young nuclear generation capacity building and integration into the European research and education area, create a guidebook for entrance of nuclear education in Ukraine as a website. Some activities will be devoted to a national contact point. It's about staff training. It's about communication offline, online communication of NCP, and supporting and improvement of the communication and dissemination tools of national contact point to raise an awareness about Euratom program. One of the key tools of our project is the NURECAB mobility program. It will start very soon from January the 1st, 2025, and it will be focused on two audiences. First one is you are researchers and representatives of research institutions and innovation entities. And the second one is a nuclear young generation. It concerns bachelor students, master students, and PhD students. All of our information we're sharing through our communication tools. First of all, the website. You can find it on the nurecab.eu, and we have 2 pages in Facebook and LinkedIn for sharing our information and sharing information about Euratom initiatives and projects. So please, you can find a lot of information on these issues. And it was short information from my side. That's all. Thank you. Thank you very much for your attention. And if you have some question, we can discuss it after the presentation of Professor Marco Ricotti. And I would like to give a floor to our main speaker today for our main topic today. Dear Professor Ricotti, please, the floor is yours.
Thank you, Sergey, and thank you, Katrina, for the invitation. I'm honored to be with you today. Let me share my presentation.
Sorry, colleagues, they mute your microphones.
А коли буде, я кажу, не знаю, що буде.
Sergey, maybe you as a host can mute the participant by yourself.
Please mute participants.
I hope that now you can see my presentation.
Yes, perfect.
Yes.
Okay, thank you. Thanks a lot. So I would like to share with you today something I know I developed as a knowledge in the last, I would say 20 years. I started addressing the SMR topic since my thesis work together with my professor, Professor Lombardi. And I continue to work on this field since that time. So the outline of my presentation, I divided in 2 parts. The first part, I would like to address the main features, the safety issues, and also the economics. And then after a coffee break, if you want, we may have a look at the war situation on SMR, especially the activities that the agency, the International Atomic Energy Agency, is carrying out. and then a focus on Europe, and then some information about Italy on that field. First of all, something about me, as Katrina is too kind. He mentioned the activities that I'm doing, but really my main activity are playing football and also playing sometimes with my band. But okay, jokes apart, let us move to the topic of today, that is SMR, but it is also the role of nuclear energy in what we learn is the energy trilemma. I have to say that Europe, up to 2 years ago, so before the Russian invasion in Ukraine, Europe was mainly concerned about the environmental issues of energy. So the topic of global warming, the topic of decarbonization, all the targets that Europe put on the table for energy, for the automotive industry and so on. But due to the international crisis that was before the war, but also with the war, we learned that there is also a strategic dependence of Europe from other countries that could be very, very dangerous. And altogether, those issues generated also a strong impact, a negative impact on the economics, on the industries, on the community, on the people. So with a high increase of the cost of life. So today we learned that energy is a trilemma, really. We have to find suitable solutions, not only for the environment, but also for other two very important items that are energy security and energy equity or affordability for the people. So the SMR may play a role in addressing all the three key topics that we should consider when we are talking about energy. So a brief overview of what's going on in the next decades, today and in the next decades at the international level. This is a slide that I'm using every time that I have a seminar on nuclear energy. These are the five different technologies that nuclear may offer for as a contribution in solving the energy trilemma. First of all, we have more than 415 nuclear power plants in operation in the world. They are of we may call standard technology, developed in the 70s, 80s, and 90s. Several of those units are reaching the end of their commercial life, typically after 40 years. They should be shut down, but what is going on is that very likely those power plants are well managed, well designed, well built. The margins of safety and operability are very high, quite good. So what occurred in US in the last 10, 20 years, for sure will occur also in Europe and in other parts of the world. The key topic is the life extension or long-term operation, typically with not a very huge investment. You may extend the life of the nuclear power plants, of the current nuclear power plants, by 10 or 20 years. So we are targeting now the lifetime, commercial lifetime of a nuclear reactor is approaching 60 years. And there is also a program in US that is called 80s and beyond. That means that some people is looking at doubling the lifetime of the current nuclear fleet, targeting 80 years. This is the current generation or the past generation of nuclear reactors that we may call standard. But today, if you want to build a nuclear power plant, a new nuclear power plant, there are evolutionary design available on the market. And they are already in operation in some countries, China, the Emirates, South Korea, India. The majority of the 63 nuclear reactors under construction in the world are belonging to this evolutionary concept. Now, what is foreseen for the end of the decade and for the coming decades? Around 2030, we should have a good fleet of small modular reactors that are the topic of today, and we will go through the main features. They are called in a different way, but in 2040, we should have also a different technology on the same concept, again, modular, again, small reactors, but based on advanced, in quotes, technology. We may call them generation 4 reactors, with the different technology that was already anyway tested in the past. And we will go through very quickly on this topic. And then 2050 or beyond 2050, some people are saying that will be before 2050, we may have the first commercial units based on fusion reactors. But this is really a challenging issue. Let's go to the main features of small modular reactors. Small modular reactors are reactors with a smaller size with respect to the traditional one that is beyond 1 giga. They are typically below or in the range of 300 megawatt electrics. What are the advantages and what are the challenges? The advantages are that several designers are using a sort of simplified approach in designing the SMR. Several of them are adopting a passive safety strategy, system based on natural circulation. That means that we are eliminating substantially the Fukushima-like scenarios. And I remember that there was only one in safety system that operated during the Fukushima accident in the first unit, in the oldest BWR unit, and it was a passive safety system. Then it was closed. The operator closed the valve, so isolated the passive safety system because it was cooling too much the reactor pressure vessel. And when they learned what was the situation on the site, they decided to reopen the passive safety system, but they ran out of electricity. So the batteries they expired. So there was no more the possibility to reactivate the only safety system that was in operation in Fukushima that was anyway a passive safety system. Another important feature of the SMRs are the modular approach. That means modularization both during the design phase and also during the construction phase. Moving the construction of the unit mainly on the workshop with respect to the site. And the last type of advantage that the SMR concept may offer is the cogeneration use. We will go through this topic in a while. I may generate not only electricity but also heat, and I may exploit that for different type of cogenerative issues. I may also, because of the safety level, I may collocate the SMR unit more close to the industrial districts. But there are challenges. The main challenge is that we need to set up an international market Otherwise, as I will explain in a while, the economics is not supporting the SMR deployment because of the size. But if really an international market will be deployed, will be set up, the economic advantage may become real for the SMR. We need series construction. We need a multiple unit construction. And last but not least, the SMR concept is promising a lot of features, but they have to demonstrate on the field that we can build and operate the SMR units on budget and on time. So this is the key issue for, I would say, for all the nuclear technologies. I mentioned 2040, more or less. We may have also the availability of advanced modular reactors. No more water-based. Typically, the main SMR concept are water-based technology. With the advanced, we are moving to liquid metal reactors. So liquid lead or liquid sodium or molten salt. So it's a different reactor physics, the more thermalized but fast neutron spectrum. And the advantages are, I would say, the same of SMR, so water-based. We have an increased efficiency. We may overcome quite easily 40% of efficiency in the thermal cycle. We may open a different option, that is the waste burner option. But for doing that, we need to separate the high-level waste. We have to recycle, and then we will burn. The challenges are for this type of technology mainly the fuel development, the fuel cycle, the economics, and the fact that I have to integrate three nuclear plants. The first is the nuclear power plant, is the nuclear reactor. But the second plant that I need is a recycling, is a reprocessing facility. And the third nuclear plant, is the refabrication of the fuel. So I need on the same site, essentially, three nuclear plants. And the first country that will be able to demonstrate that in the coming years will be Russia. We have different concepts of SMR and AMR. We may have a sort of clustering of those concepts by their use or by their site. For example, we may discriminate the SMR, AMR concept in terms of land-based nuclear reactors or marine-based or transportable nuclear reactors, or in terms of electricity and heat production versus the use of SMR or AMR for propulsion. And this could be a very interesting market because the cargo ships are emitting not a negligible quantity of CO2. Now, due to the geopolitical issues, the cost of transportation of goods increased a lot. Also, the time of transportation. So a nuclear reactor as a propulsion for cargo ships is something that is very attractive today. The last type of clustering could be with respect to the grid. Some SMR units may be connected to the grid, or others may be off-grid, related to remote areas, for example. Or we may set up the concept or discriminate the concept of the SMR AMR by reactor technology. So we will have light water reactors. We may have integral layout versus loop type, classical loop type layout for PWRs, for example. But we may have also sodium cooled, lead cooled, fast reactors, molten salt reactors, high temperature gas reactors, and microreactors that may use different technological solution. For example, heat pipes instead of a cooling system in the classical way. Let me put some focus on the integral PWRs because they are a good percentage of the SMR concept that are proposed today. And we spent a lot of years on studying and putting research on this type of concept. You see here what you know already well, the classical PWR layout with the reactor pressure vessel, the primary piping, the steam generators, the pumps, and the pressurizer. So let's imagine that we may put all the large components that are outside the reactor pressure vessel all inside one single larger, taller reactor pressure vessel. This is the integration. In this way, we may eliminate the large primary piping penetrations, and all the external primary components are included inside the reactor pressure vessel. So we end up with a PWR still, but with a very compact layout. The other advantage is that we may use a compact containment, and we have a smaller primary building and a smaller footprint for the power plant. This is an example of comparison between the containment, the steel containment for AP600 is a classical two loops PWR developed by Westinghouse, and this is the size of the containment. It's a steel containment, 40 meters in diameter and almost 60 meters in height, versus one concept that we developed with Westinghouse in the past, the IRIS integral reactor concept, with only half the size, so 335 megawatt electric, but with the very small and compact containment, steel in steel, 25 meters diameter, the sphere, so 1/6, 1/8 of the volume of the containment. The integral PWR is usually putting all together the steam generators, the pumps inside, also the internal control rod drive mechanism. Not all the concepts are like that, but this is the maximum level of integration that we may reach. So we have penetrations of the reactor pressure vessel, but not primary penetrations. They are secondary side penetrations. So we have the core, the bottom, we have a large riser. On top of the riser, we have the control rod drive mechanism. And then in the annular region, we have on top here the main circulation pumps. Then in the annular zone, we have the steam generator modules, and then we have typically quite a large downcomer in the lower part of the reactor pressure vessel. If you are adopting a very compact containment, like in this case, but it is also the same for NURECAB, for example, in some cases, we may adopt the typical BWR containment strategy, that is the pressure suppression containment, not a pressure containment. And this is what we developed for IRIS with the pressure system to suppress the steam in case of a small break lockup with the pressure suppression pools. But really, in terms of SMR concept, if we look at the integral PWR, this is not really a brand new concept, because a very similar concept, integrated, was in operation for more than 10 years on the German ship Otto Hahn, was a cargo ship, using an integral PWR, 38 megawatt thermal, with helical coil steam generators, a solution that is largely adopted by several SMR concepts today. And in the 80s, at the end of the 80s, there was another project by UK, by Rolls-Royce. It was the SUR, safe integral reactor that was very similar to the Otto ship nuclear reactor, with again helical coil steam generators, the modular approach, with the pump not inside but connected directly to the reactor pressure vessel. About the fuel and fuel cycle, usually for the SMR, based on water-cooled technology, we have not really a sensible difference from the current generation 3 PWRs. So the enrichment is usually the same of the current PWR, so less than 5%. In some cases, some design, they are targeting HALEU, high assay low enriched uranium, so slightly below 20%, 19% is the typical enrichment. But this is not an easy task because today the high assay low enriched uranium is not really available on the shelf. They are usually adopting a shorter fuel assemblies, fuel rods. So typically half the height of the classical PWR or BWR fuel assembly. And also some concepts are proposing a boron-free core. It is a challenge for the control rods and also for the burnable poison, but it owes the advantage of eliminating a huge quantity of ionic exchange resins for the control of the boron content, that for the decommissioning is a challenge anyway. About the fuel cycle length, several concepts are targeting an extended fuel cycle, typically around 48 months. So almost doubled the current, or more than doubled the current fuel cycle length. And I put here a table comparison for some of the integral PWR concept from Argentina, US, China, and others, and you can see the main differences. Only in few cases, the Russian technology, they are using 90% more or less content of U-235, but typically the enrichment is below 5%. Other opportunities, or the main opportunities for the SMR. I would say that SMR could be the preferable solution for grids of electricity of limited size, but also could be the preferable solution for remote areas. It is also, from the economic point of view and the financial point of view, a good solution for those utilities that have limited financing capacity. They cannot afford the endeavor of a multi-billion unit cost, like for the large nuclear power plants. That means around more or less 10 billion, euros, or more than $10 billion investment for a single large unit. Because of the size and also because of some features of SMR technology, we may more easily integrate nuclear with renewables. That means that we can avoid a system cost for the country related to the energy storage and the grid development. That means we are reducing the system cost for the community. As I mentioned before, we may open the window on cogeneration application. So using electricity, producing electricity and heat for hydrogen production, for example, with the high temperature electrolysis, for district heating, for desalination, to produce biofuel, for example, for aviation, and also to have hydrogen or thermal energy storage. because of the safety features that we will address in a while, we may also try to collocate or to site the SMR units closer to the industrial districts in order to support the development of industrial sectors that are typically quite energy intensive. I'm thinking about the steelers, the cement industry, the pulp industry, the glass industry, ceramic, and other industrial sectors that are energy intensive. And it could be a challenge to decarbonize those sectors. But, and this is my personal opinion, the SMR could be also a good opportunity for the nuclear sector, for the nuclear supply chain to retrain. And I'm thinking mainly on the Western countries, US and Europe, while in other countries, China, Russia, India, South Korea, they are well trained. They don't need to retrain the supply chain. But this is not the case for the Western countries. So SMR could be also an opportunity to accelerate the retraining of the whole nuclear supply chain. Now, let us look at the safety features, the main safety feature for the SMR concept. In some cases, for example, for the integral PWR, we have a very interesting safety features. As I mentioned before, if we are integrating all the main components into a taller and in some cases larger in diameter reactor pressure vessel, we are eliminating by design the large loss of coolant accident because we will not have large piping penetrating the reactor pressure vessel. If we are considering a full natural circulation PWR, integral PWR like CAREM in Argentina and NuScale in US, in that case, we don't have the pumps. But also in the other concept, we may have pumps located internally the reactor pressure vessel or pumps that are directly connected to the reactor pressure vessel. That means we are adopting canned motor pumps. If that solution is applied, we would have no leakages at all, potential leakages, or we have a reduced probability of leakages by the pumps. If we are integrating also the control rod drive mechanism, we may eliminate by design the rod ejection accident from the reactor. Okay, the first three items are mainly related to integral PWR concept, but the other two are applicable to all the SMR concept. Several of them, they are adopting passive safety systems. That means that we are eliminating by design the Fukushima-like accidents. And if you are using a solution for the containment, the steel containment that is directly submerged in a water pool, or it is cooled by an external spray of water or a natural circulation of air, we are again eliminating by design the long-term ultimate heat sink accident. Since we may target a higher level of safety for this type of SMR concept, we may have also the possibility to discuss with the safety authorities in order to reduce the emergency planning zone. And in some cases, they are claiming that for their SMR, the emergency planning zone is reduced to the fences of the power station. That means, roughly speaking, is 500 meters or maximum 1 kilometer radius area from the reactor core. We can try to reach that goal because we have a reduced source term and we are adopting passive safety system. So there is a high potential. It's not granted, but there is a high potential for a discussion with the safety authority in order to reduce the emergency planning zone. And this is an important feature for the stakeholder engagement, the public engagement in the nuclear technology. There was a technical document issued in the recent past by the Atomic Energy Agency, the International Atomic Energy Agency. We developed an approach, a procedure in order to try to demonstrate that it is a probabilistic and deterministic approach. If you want, you can download the paper from Progress in Nuclear Energy or download the tech document from the agency site. If we are targeting the integral PWR concept, very likely we will have a larger diameter reactor pressure vessel with respect to the core. That means we have a large gap of water between the barrel and the reactor pressure vessel boundary. You can see here in this picture the typical radial position of a classical PWR. So we have the core, the neutron reflector, and the core barrel. If we target an integral PWR, we did that exercise for Iris. We have quite a thick downcomer, quite a large downcomer. So you can see here the neutron flux trend. You are gaining, I would say, 5 orders of magnitude in reduction of the fast neutron flux on the vessel. That means you are reducing a lot the embrittlement probability of the reactor pressure vessel. So essentially no embrittlement, that means no surveillance is needed. The decommissioning will be highly simplified for this type of approach. Other innovation in terms of safety, if we are adopting passive safety systems, I would say mainly for integral PWRs, but not only. For example, for the core cooling system, we may inject water also by gravity in a passive safety system. The decay removal system could be based on natural circulation on two-phase flow in closed loops. We may target an in-vessel co-retention strategy in case of severe accident, if we can flood the reactor cavity. The diver shutdown system is, I would say, a classical boronated water injection, but not in an inactive system, but by a passive system, so by gravity. And if we are adopting a steel containment, we may have a steam condensation by external water or air, as I mentioned before, if it is submerged into a pool, or if we are using natural circulation by water or by air outside. The compact containment, I show you the slide at the beginning. The slide in the beginning, we may adopt the pressure suppression BWR, classical BWR type containment, even for a PWR integral concept. And this is the case for CAREM, the Argentinian design. And you see here a pressure suppression containment that is very similar to the BWR concept. In case of the steel containment, we had a past option, newer, now the design has changed, or the current design of NUScale that is using a steel containment, the steel with the reactor pressure vessel, the integral PWR inside are all submerged into a large pool with the heat exchanger in the pool itself. that are operating in natural circulation. With respect to the size of the SMR, we may target a very interesting safety feature like in NuScale, since the size of the NuScale module is very, very small. It was at the beginning 55 megawatt electric. Now they, because of economics, they upgrade the concept to 77 megawatt electric. I would say that it's still a challenge from the economic point of view, but from the safety point of view, it may offer a very interesting solution because the coolability of the water reactor after the scram, after the shutdown, is carried out at the beginning with the natural circulation by water after the first day. After the third day, in a range of time between the third day and the 30 days, the cooling system is ensured by the evaporation of the water into the pool. Imagine that we are not replenishing the water into the pool, so no human intervention. The reactor is shutdown mode, without electricity, without human intervention. The system is the pool, the water in the pool is cooling down the reactor pressure vessel just by evaporation. And after 30 days, the decay power is so low that once the water is evaporated, completely evaporated, just the natural circulation by air is able to cool down and to keep in a safe mode the reactor core. Obviously, this is something that is allowed by the adoption of water, the steel containment, but also because of the very small size of the module. The typical passive safety system that are adopted for the decay removal system or residual heat removal system are passive safety system directly connected to the steam generator with the water pool or with the air cooling, or are directly connected to the primary side. So in the first case, I remember that the steam generator is inside the reactor pressure vessel in case of the integral PWR. It would be outside if it's a classical loop type. In the second case, we have the natural circulation loop that is directly connected to the reactor pressure vessel. And these are some examples of the integral PWR concept. This is the CAREM, this is the Argentinian one. The passive residual heat removal system shows that there is a condenser that is dipped into a pool, is the number 3 here on the right side of the slide. And this condenser is directly connected to one module of the steam generator that is inside the reactor pressure vessel. The same solution for NuScale. So they have a classical condenser that is placed into the large pool. And this condenser is closing a natural circulation loop through the helical coil steam generator that is inside the reactor pressure vessel. A similar solution was designed recently for the SMART, the Korean SMR, when Saudi Arabia became a partner of the project. Saudi Arabia asked to CAERI, to the Korean Atomic Research Institute, to modify the original design of SMART, that was an active-based safety system strategy, into a fully passive-based safety system strategy. So again, they connected a condenser and an external pool to the steam generator modules that are also in this case are helical coil steam generators. ACP100, this is a unit that is already under construction in China. The same solution. They connected the residual heat removal system to a condenser that is in the spent fuel pool, and then they are recirculating the primary fluid directly to the integral reactor pressure vessel. There are also challenges in demonstrating the capability of those passive safety systems. Let me mention at least two challenges from the thermal hydraulic point of view. First of all, the seal containment. You see that some concept of the SMR are adopting this seal containment solution, very effective in terms of safety principle, but a challenge from the point of view of demonstration to the safety authority, because typically we are using large steel containments. And if you look at the diagram on the right side, the upper right side of the slide, in terms of Rayleigh number, the non-dimensional number, the current limit of the correlations that are available today on the heat transfer coefficient in natural circulation is in the order of magnitude 10 to the 12. But because of the diameter of the containment, it is typically 10 or 20 meters. The characteristic length is that one. We would need heat transfer correlations that are related to Rayleigh numbers that are 2 or 3 orders of magnitude more. And this is something that we studied for a flex blue concept, the French concept of SMR into a hull, a sort of hull of submarine. Because of the large dimension, more than 15 meters diameter of the hull, we end up with this type of situation. So the only way was to investigate this solution with CFD. But that means that we need experimental activities to validate that CFD analysis. Another challenge from the thermohydraulic point of view is the large downcomer that is very positive for the thermal inertia, very positive for the neutronics point of view, the embrittlement, the very reduced embrittlement of the reactor pressure vessel. But it means that we would have a large turbulence in that area. We had the problem of investigating the level of mixing of hot water, cold water, boronated water, fresh water into the downcomer in order to guarantee that we will have a good mixing of the water at the inlet of the reactor core to avoid a hot spot in terms of reactivity into the reactor core itself. That means that, and this was an activity that we performed in the recent past for IRIS design. We had to set up an experimental facility to investigate the mixing, but we had also to develop nonlinear eddy viscosity models for the CFD analysis. So it is a modeling and experimental activity that is required by the new layout, the new solution that some SMRs are proposing. Not only modeling, I mentioned the experimental activity. The experimental activity is fundamental, especially if we want to license the SMR concept. We are typically approaching two different sets of experimental activities. The first group is the so-called separate effect test facilities. They are devoted to the fuel investigation and also the investigation of the components that are typically integrated. So the pumps, the steam generators, the control of dry mechanism, the pressurizer. I need those separate effect test facilities to demonstrate the capability of the code to predict the real behavior of that integrated systems. I have also to investigate the safety system, typically the passive safety system that I'm using in natural circulation in two-phase flow. But at the end, to convince the safety authority, I have to show them not only separate effect test facility, but very likely also an integral effect test facility. That means one large facility that is simulating all the system, the primary system and the safety systems. Typically with a large scale, I need to demonstrate the capability of the codes to model to simulate the integration of the components and the interaction between the primary system, the safety system, and in some cases, even the containment, if I'm adopting the steel containment. What are the main goals? The main goals are to test the safety effectiveness of the concept and also to test the performance of some components, to develop the technology. The second goal is to validate the codes and the models for the licensing process. But these type of facilities are very useful also to train and to educate. Because if we are not a country that is developing that concept, we need to become an intelligent customer. Here, some example of separate effect test facility. This is a facility that we set up in Italy, in the SIET lab some years ago for the ARIS project. It was the simulation of the whole passive safety system based on the helical coil, internal module, steam generator, and then a condenser outside of the reactor pressure vessel, but within the steel containment to set up a closed loop without a pressurizer, is a pressure sliding system. And we investigate the performance and also the map of stable behavior of the system in order to investigate the natural circulation. But we will need also integral testing facility, and this is an example of the Chinese colleagues for the ACP 100. They set up one of the largest integral effect test facility in the world. It was 1-to-1 full scale in 8 because you cannot scale down natural circulation. So you have to set up a full scale in 8 system. Also full scale in pressure and temperature. But anyway, with the large scaling, 1-to-37 in volume, that is one of the largest facilities in the world, and 1-to-100 in power. Typically, to give you an idea, in SIET, they set up the integral testing facility for the AP600, AP100 Westinghouse large reactor. And the scaling factor for that large facility was 1-to-357. So here it is one order of magnitude larger for testing the integral PWR. And also the smart facilities, the integral test facility for smart, the Korean concept was similar. Was an integral loop, full scale in 8 pressure and temperature, and 1-to-49 in power and volume. One approach, very interesting approach to the safety analysis that we may use for developing this SMR concept is the risk-informed approach. So the integration between deterministic analysis and probabilistic analysis. This is another experience that we had for IRIS. We had the design and safety analysis team addressing the deterministic approach. And then we have a PSA team, a probabilistic safety analysis team. The design team was providing data and boundary condition to the PSA team. The PSA team performed the preliminary PSA analysis, identified the weak points in the design, suggested or gave this type of information to the design team. The design team changed the design, provided new data to the PSA, and that loop was performed several times during the years, during the development phase of the concept. And this is the result. So we start with the estimated core damage frequency for iris that was 10 to the minus 6. And every dot is a change in the iris SMR design. We work a lot in 2003, 2004, 2005, changing, having this loop of design development, PSA analysis, design change, PSA analysis, and so on. After several changes, we end up with a core damage frequency that was reduced by 2 orders of magnitude. So from 2 10 to the minus 6 to 2 to 10 to the minus 8. Even after including the external events, the seismics, we decided to go with the fully seismic isolated primary building. So this is quite an interesting result of this type of approach that is anyway adopted by several SMRs today. Let me go quickly through the last part of this first part of the seminar on the economics. Let me give you a picture of what is the situation today for the large reactors. If you look at the Western countries, Europe, mainly the French design, and US, mainly the US design. If you look at the EPR built in Olkiluoto, but also Flamanville that recently was connected to the grid. And also if you look at Vogtle units 3 and 4, but also VC Summer units, we see that they started planning the construction of the large units, targeting 5 years, targeting 3.5 up to 7 billion euros or dollars. But the real story was quite different. All those projects, they had more than 7 years of delays and more than 80–90% overrun in the budget. In some cases, like Olkiluoto, they almost tripled the cost of the construction of the unit. In one case, it was even worse. This is summer. They started building the first AP1000. After spending $7 billion, they decided stop. It was stopped also in Vogtle, but after 2–3 years of suspension, they completed the unit. Today, the VC Summer is still stopped. And it is not clear what will be the final decision for that. Is that a problem of the nuclear technology? The answer is on the right side of the slide. If you look at Baraka in the Emirates, APR 1400 is not the same technology, but is very similar. It is the South Korean technology. But if you look at Sanmen and Taishan in China, exactly the same technology, AP1000 and EPR, built and now in operation since several years, without the same delay, without the same extra cost. So, is the nuclear technology the problem? No, because we have exactly the same technology. I'm not saying perfectly, but almost in a very reasonable time frame and budget built exactly the same evolutionary technology that was completely failed in the Western countries. And one, if I'm saying failed, means strictly speaking failed, because both Arriva and Westinghouse, they were in bankruptcy because of this negative experience. So now Westinghouse is owned by a Canadian investment company, and Arriva is now in EDF. So he returned to the original name Framatome. It is in EDF. Okay, this is one of the reasons why SMR could be attractive. SMR, if we are designing and building a unit that is more simple, is smaller, it is modularized, we should be able to build the SMR units on time and on budget. This is a sort of promise, but we have to demonstrate that on field. On the other side, we have a negative feature for the SMR. The universal law, not only for nuclear, but for all the industrial system, is the economy of scale. And this was the trend that nuclear followed since the beginning, since the 60s. The first units were 100, 200, 300 megawatt electric, and then they developed the 600 megawatt electric plants, and then the 900 megawatt electric plants, and then the 1200s, the 1600 megawatt electric units. So following a universal law that is economy of scale. So if now we are with a specific cost euro per megawatt with the 1200s large reactor, if we want to go back to smaller scale, we will have a disadvantage given by the economy of scale that would move the specific cost of the SMR units at a very high value. So from this point of view, it would be a nonsense to go with the SMRs. But what could be the features of SMR that may reduce this disadvantage, that may bring down the cost, the specific cost of the SMR to something probably even larger, but competitive with the cost of a large reactor? We have at least 5 features. First of all, if we are deploying SMRs, we are typically deploying more units on the same site. So multiple units on the same site is reducing the specific cost. In this way, we will accelerate the learning process. So the learning curve is reached more easily with more SMR units than one single or few large reactor units. The third, modularization. We may redesign the SMR concept, the construction phase, moving to a modularized approach. So different modules for building the same SMR units. It is an engineering strategy that is already adopted since several years in the oil and gas industry, in the maritime industry. So it's not something that is completely new, but it is new for the nuclear sector. Then we may decide for future to scale the investment. I may decide to start building the first SMR units and then the second, and then according to the economic boundary condition, I may decide to reduce the pace, to delay the construction, or to accelerate the construction. So I may scale the size of my power plant according to the boundary conditions. And last but not least, I may decide to simplify the design, the construction phase, reducing the cost of the unit. So with those 5 features, if I'm good in exploiting them, I may reduce the penalty, the disadvantage of the economy of scale. In this case, I may exploit also, you see on the top right part of the slide, a diagram that we produce with the code that we developed for the economic evaluation of SMR deployment. You see the investment for a utility in the construction of 2 SMR units. And in green, you see the equity that is used by the utility. In red, the debt, but in yellow, the self-financing. Because after deploying the first unit, I'm starting selling the electricity, and part of the gain that I'm getting from the selling of the electricity of the first unit could be invested in the construction of the second unit, and so on for the third and the fourth. So I may exploit also a self-financing approach for the deployment. So briefly speaking, we have to move from the economy of scale to the economy of multiples, and the typical comparison is between a chicken egg, a classical small chicken egg, and an ostrich egg. An ostrich egg is something that is very large, quite expensive, very massive. So from the point of view of the industry and the supply chain, we have uncommon suppliers and few suppliers of those large components and large units. While for the chicken egg, if we reduce the size and the complexity of the components, we may target a more standard product. We may have more standard suppliers that are already trained, so they are already experienced, and I may enlarge the number of suppliers that could feed my design and my deployment. Okay, I don't know whether you want to stop here for a while, for 5 minutes, or if you want, I can continue. Please, Katerina or Sergey, let me know. I see also that there are some questions on the chat, right?
Yes, yes.
Okay, we may start answering the questions on the chat.
It's Marco, up to you. If you feel that you can continue, I think that the audience
Okay,
is
we
pretty
can continue,
happy
no
with that.
problem.
But maybe about question, we can give an answer right now, and after the second half, the second part of questions.
Okay. I see. Olex, how many system structure components are first of a kind, commercial grade components, and or SSC with proven design? Do you have any data? No, I don't have a specific data, because this feature is specific for each SMR design. It depends on the layout, on the real design of each SMR. So we cannot say in general, we cannot give numbers in general. We have to look at the specific design. But this issue of commercial grade components is something that is very important. There is an initiative on that issue by IAEA. Pekka P, one of the managers, one of the officials of the agency, is working on this topic since several years. If we want to accelerate, I would say not only the SMR deployment, but also the large reactor deployment, we should try thinking about the adoption of commercial grade components, high quality, also in the nuclear sector. This is something that may accelerate the deployment. So qualification is an issue, but this is an important topic. Igor, how was the upper level of 300 megawatt electric chosen for SMR's identification? What about the serviceability of main components in the integral PWR SMR design? Sorry, I'm not catching the question, the first part of the question. What do you mean with how was the upper level of 300 megawatt chosen for SMR identification?
You mentioned that according to the classification of small modular reactor,
yes.
its power should be less than 300 megawatt of electrical.
Okay, there is, thank you for the question. There is not really a very strict limit. So 300 megawatt electric is an order of magnitude. Obviously, if you go with 600, it is not a small reactor. I would say is a sort of intermediate size reactor between the small and the large. But 300 or 200 or 400 megawatt electric is anyway a value that we may consider as a sort of limit for SMR. But there is not really a strict limit. It's more an order of magnitude. So if you want to propose a 350 megawatt electric, it will be anyway an SMR or even a 400. And it's something similar to what it is already occurring because Rolls-Royce, we will discuss in a while, the Rolls-Royce PWR new design, they are proposing this as an SMR, and it is a 400 megawatt electric size. So there is not a strict limit. What about the serviceability? This issue of the integral PWR and serviceability is important. In several design of integral PWR, they are putting an effort to push in-service inspection for those components that are inside the reactor pressure vessel.
Right.
Because it is not practicable to ask every time in order to perform inspection to shut down the reactor and open the reactor pressure vessel to remove the components. So for example, for the SMR steam generators modules, several designers are thinking about the in-service inspection. We did that exercise for IRIS, and out of more than 700 actions for inspection, this was a work that was performed by MIT with the TVA, Tennessee Valley Authority. It was a utility. They moved, I would say, 90% of those requirements to in-service inspection. Only 19 remained, and they were addressed by TVA. So for IRIS case, we may say that 99% of the activities could be moved from a classical inspection procedure to in-service inspection. But this is very important for the integral PWR. I fully agree. Then Igor, what were the major contributions in reducing CDF based on risk-informed designing concept? One large contribution was the adoption of seismic isolators for the main containment building, for the external events. For the internal events, it was a redundancy and diversification of the passive valves, so the failure to save valves that were connected to the safety systems. This was something that was already demonstrated by Fukushima. If you remember, I mentioned that in the Fukushima accident, there was only one safety system that operated after the tsunami in Unit 1. It was an old, I would say, condenser system that was activated by a valve that was operated by the operator, and it was open by electrical signal. If they had substituted that classical valve with a fail to save valve, probably they would have saved at least Unit 1. Because with a fail to save valve, the valve is kept closed by the electricity. If you are losing the electricity in a loss of offset power or a station blackout, the valve is opening and you cannot close. So this is something that was adopted, and we see that by using this type of solution, we improved a lot the core damage frequency. We reduced a lot the core damage frequency.
Okay, thank you. And one more follow-up question. What
Please.
about the optimal redundancy? You just have mentioned about redundancy. What was the most optimal one based on your research?
We saw that really for the passive safety system, to go with the strategy 4, like it was
Oh,
used by
okay.
the
Yeah.
active system in EPR, is not
Yeah.
needed.
Yeah.
3 is more than enough, I would say.
Very good. Thank you. This is very important question, you know.
Yes. Yes, we don't have to increase too much the number
Yeah, right.
of the system. Otherwise, okay, we are not really improving too much the safety level, but we are increasing a lot the cost. So we had to find a good trade-off.
Yeah, thank you. Thank you very much.
Thank you to you. And then Sergey, could you name the existing project of fast small modular reactors then when the creation of the Industrial Alliance of SMR was announced in Euratom? Only thermal SMRs were discussed as far as no. I will go. I have some slides on this. Not only the SMR light water based concept were selected by the alliance. We have also lead cooled fast reactor, and I would say very likely in the second round of selection of process of design, we may have also high temperature gas reactors and also sodium fast reactor probably. Today, only lead cooled and molten salt reactor were selected together with the light water SMR. Okay, good. Now, let us move to the international, European, and Italian point of view. I'm using some slide that I took from the agency. A couple of slides about the SMR that are already deployed or are at advanced development status. Only academic Lomonosov and only HTR PM in China, they are in operation today. The only SMR that are in operation. One is a PWR, very compact PWR, not an integral PWR, but a very compact PWR. And the second is a high temperature gas reactor with a pebble bed with the microspheres inside the macrosphere. What are the SMR under construction today? ACP 100, very advanced in China. Brest, that is a lead-cooled fast reactor, and CAREM in Argentina. Unfortunately, Argentina suffered a lot of political, economic issues, so they are suffering a lot of delays in the construction, but the design is completed. So the only critical issue for the Argentinian colleagues are the funding and the stability in the political strategy. Some units are already in construction today. The Rhythm 200, but it was already working on the icebreakers. Voyager, that is the new scale, is not yet under construction. Probably the first of a kind could be built in Romania. Then we have Hermes, a molten salt reactor with TRISO. Is a demonstrating facility of Kairos Power. Natrium is the concept funded by Bill Gates in US. Is a sodium fast reactor. They are under the licensing phase. BWRX 300 is a small BWR, fully natural circulation. Is a, let's say, is a short, is a reduced unit by ES BWR of GE Hitachi. And they will start to build this nuclear reactor first of a kind in Canada. Ontario Power Generation is beginning the construction in Canada next year. And this is my short list of what I personally consider the most advanced concept for integral PWR. But I want to remember that there are today more than 90, I have to update that number, more than 90 SMR, AMR, microreactor concepts or design that are under development in the world. You can download the booklet that IAEA is periodically updating. There will be an update, I think, next year. And I put an example of the integral SMRs, CAREM, NuScale, Rhythm, ACP100, SMART, NUART, but you see a green curtain on that. I will explain in a while. BWRX, and I put IRIS because it was our concept that we developed since 2000 up to 2008 with an international consortium. And I put the list of some of those concepts with respect to the size. So we have a large range of modules from just few tens of megawatt electric for CAREM. It is a demonstrator anyway, it's not a first of a kind commercial, to the 77 megawatt of NuScale, the 50 of Rhythm, 100 ACP 100 for SMART. Now the Koreans are developing another concept of integral PWR, no more developed by the research body, but from the industries. The name is ISMR, Integral SMR. NUART was originally 170, but now they are changing their mind. They will upgrade the size. The largest size is for BWRX 300. You can see also the forecasted years of operation. It is 2030, even before 2026 or 28 for ACP 100 and for Rhythm. But the main target is usually 2030, the first years of 2030s. What are already in operation? I mentioned the Russian and the Chinese. The top of the slide is for integral SMR, but we have also some loop type SMRs under development today. AP300 for Westinghouse in US, the Rolls-Royce SMR that is a 3-loop type, and NUART 2. EDF decided to move from NUART 1 concept to NUART 2 very recently, a few days or no more than 1 week ago. They decided to move their mind from an integral to PWR to a more classical few loops PWR in order to reach the market more easily and more quickly. They think several countries are thinking about SMR deployment for their strategies. So the French colleagues, they decided to change the concept in order to accelerate the development and to reach the market on time. And this is quite interesting approach. I will have a news also in the next slide. So today we have light water-based SMR, that is the majority, 25 land-based and 6 marine-based. But we have also 14 concepts of high-temperature gas reactor, 11 concepts of fast reactors, liquid metal, lead or sodium, 10 concepts of molten salt reactors, and also 6 concepts of microreactor. Micro means below 10 megawatt electric size. what is going on in the agency? The agency, since several years, they are putting a lot of effort on that. They have now a dedicated portal. It's a sort of one-stop shop initiative. If you go on the portal smr.iaea.org, you will find a huge number of information on that. They decided to have a single platform for the agency. You know, the agency is subdivided in several divisions. I will remember 8 divisions. But the SMR concept is a sort of cross-cutting concept. So they decided to offer to the member states a sort of one-stop shop. So if you need some information on the SMR, please go on the agency, go on that platform, and you will have access to a different set of information on all the different topics, from safety to security, safeguards, fuel cycle, economics, technology assessment, and so on. As Katrina remember at the beginning, I'm also chairing since 7 years, 6-7 years, the technical working group that the agency launched in 2018 on SMR. We have now 20 member states participating. Ukraine is a member of that. I put the name of the person that usually is participating with in our meetings from Energoatom, Mr. Ilya Krasnuka. And we have periodically meetings on different topics. We have today at least 3 subgroups related to the user requirement criteria, the research technology development, the industrialization, and we usually perform activities on those topics along the year. The agency developed a lot of initiative, not only the platform, but also a recent initiative was the NESI, the Nuclear Harmonization and Standardization Initiative, with 2 large groups. One is related to the regulators, and another group of activities is related to the industrial side. But you can see on the left side of the slide all the set of initiative ranging from the fuel to the economics that the agency is performing. And I want to highlight the fact that next year the agency will launch also the first SMR school for the member states. They will have 1 or 2 initiatives during the year. 1 or 2 of those SMR schools launched in different countries. So you see anyway the different topics that are addressed, from the legal framework to the safety and security, the safeguards, the infrastructure development, and the technical cooperation. We had this year in October the first SMR international conference organized by the agency. It was really a big success because we had more than 1,300 participants in person and more than 1,000 connected online. 95 member states attended, 17 international organizations, almost 300 papers presented. And you see here the distribution in terms of countries. The participant age, very interesting, because the more than 30% was young, I would say, experts from 30 to 40. Also the number of papers, the technical section, some numbers that are anyway explaining that it was the first, but a very impressive success. Was not expected by the agency, this type of response from the member state. There is a lot of interest on the SMR issue. Now, let us go to the closure of the seminar, then we will open to the discussion. What's going on in Europe? In Europe, I think that we have a growing interest towards nuclear in general, included SMR. I put the list of the countries that in 2023, 2024, different governments, they declared interest on large reactors. All the countries that are mentioned here are interested in large reactors, but several of those countries are also interested in SMRs, few of them in AMR or microreactors. Nuclear Europe performed a study on the potential market size of SMRs in Europe, and the numbers are quite interesting because it is, roughly speaking, as an order of magnitude, 10 units could be possible by 2035, and then after 2035 to 2050, there is a potential market of more or less 10 units per year in Europe. So if this will be the case, it will be that a series production is really possible. So the economics of SMRs could be really practicable. From the point of view of Euratom and research activity, this is the list of initiatives, and I think that some Ukrainian colleagues are already involved on those projects. For example, Elsmore, Tandem, SASPAM about the safety, the severe accident. ESFR Simple is for the sodium fast reactor. Anselmus is for the liquid metal SMRs. EcoSense is for the economic and social involvement for SMR. SUN is for the non-electric applications. And the last project that was launched this year is the Easy SMR project. For the first time, more than 10 million euros were put on a single call. And the key target here is the testing of passive safety system and components for the SMR concept. Not only that, but also testing. For Elsmore, the experimental testing that was performed was in SIET Labs in Piacenza, in Italy, for the testing of the passive safety system. It's a closed loop using a new concept of steam generator. Was a compact plate, a very compact steam generator. An experimental facility was set up at scaled geometry, scaled power, but full pressure, full temperature, and full heat. The Tandem project is addressing the topic of hybrid energy systems. SMR used to produce hydrogen, to be coupled with variable renewables, and also to produce desalinated water or to distribute heat to the communities. We developed an open source library in Modelica to be able to simulate this complex energy system. We performed some techno-economic optimization of that hub of energy, and we performed also safety analysis of this coupling SMR with the other plants via classical system codes. What we learned is that there is the possibility to couple SMR, even AMR. This is a study that we performed with the lead fast reactor in different configurations, with the cogenerative approach, with the desalination approach. We can find the tool and the possibility to demonstrate the effectiveness of integrating an SMR plant within an energy system that is mainly managed by renewables that are in a way intermittent. The topic of SMR Alliance. This year in May, we launched the European Industrial Alliance for SMR in Europe. The main target is to foster, to support the early deployment of SMR in Europe. The target is 2030 of the first years of 2030s. So the target is an industrial target. The number of members at the beginning was slightly less than 300. Today are more than 320 members. 5 technologies are approached: the light water SMR, the advanced SMR. 24 or 25 design are now proposed from light water SMRs for electricity production, some light water SMR for district heating only, so specific design for district heating. We have advanced lead, sodium, molten salt, high temperature gas reactors. We set up the initiative with 8 technical working groups that are cross-cutting activities, and then vertical project-based working groups for the project. These are the 8 technical working groups that are targeting the industrial applications, the technology and research, the supply chain, the skills and human resources, the public engagement, the nuclear safety and safeguard, the fuel cycle and waste management, and the financing, that are all very important topics for any type of SMR. And before the end of this year, the governing board identified the first batch of project working groups. And you see here that we have light water based SMR. We have Rolls-Royce SMR, UK. OSG is a Poland consortium targeting the deployment of the BWRX 300, so USG Hitachi. We have a NURECAB 2, the new design, the loop type water SMR. And we have also the Last Energy is a very small 20 megawatt electric PWR loop unit, so very, very small unit. But we have also the Steady Energy, Calogena, that are the French and Finnish district heating design. So very small reactor, but only for district heating, so low pressure, low temperature. Then we have 2 AMR lead fast reactor with a strong Italian participation. One is Nucleo, is the startup, and the second is the consortium of Ansaldo Nucleare, Enea, Raten, Romania, SCK Sen, Belgium, for the European SMR lead fast reactor. And the last concept is Horizon, is a molten salt concept. So this is the list, the first list of SMR. Sorry, I forget RoPower, that is a Romanian consortium for the deployment of NuScale. So this is another SMR light water based concept. This is the first batch, but next year, around mid of next year, mid of 2025, there will be a second round. So other SMR concept could be identified by the SMR Alliance. So it's not a closed group, but anyway, it is still a large group of concepts. One important feature that occurred this year and in 2024, in 2023, launched by the NURECAB concept, they were quite effective in letting different safety authorities to work on the analysis, on the preliminary evaluation of this SMR concept. At the beginning was only ASN, the Safety Authority of France, STUK, the Safety Authority of Finland, and the Safety Authority of Czech Republic, SUGB. But this year, other 3 safety authorities joined the group. It's the joint early review activity: Poland, Netherlands, and Sweden. And this is a very effective approach, in my opinion. Is the only way to foster a common understanding of new SMR reactor projects. We cannot force the safety authorities to work together and to have a single licensing procedure. This could be a future goal, for example, in Europe, to have only one single safety authority, or to have different safety authorities, but with a single process. This is not the case today because of the legal issues and political issues. But the most effective way to foster the common understanding and to accelerate the licensing of SMR is this approach, in my opinion. The latest news last week was that EDF confirmed the interest on an SMR design. They abandoned the original integral PWR NUARD project. They are launching a NUARD 2 project based on a more classical loop type, and they are open to partnerships. So they would like to offer this project as a real European project. It is the only European project now from the SMR light water reactor point of view in the alliance. This could be something that other countries may look at. From my point of view, I'm trying to push Italy to seriously consider to become a partner of this NUARD 2 project. I think that you may think about joining this effort, because they are in the development phase. So the project is not yet closed. Like in NuScale, like in other design, the project is already closed. So you can only become a customer of that technology. In this case, there is an opportunity to become also a developer of an SMR. So I think that is something that we should consider seriously. Last comment is about Italy. Italy is not a nuclear country today. We were a nuclear country in the 60s, 70s, up to Chernobyl accident. We had 4 nuclear power plants in operation, plus 1 under construction. They were small reactors, not modular, but they were small reactors, no more than 100, 200 size for Latina, gas graphite Magnox type reactor, for Garigliano, BWR reactor, for Trino, PWR reactor. There was one large reactor, 800 megawatt size BWR in Caorso. And then there was another large BWR reactor under construction in Montalto di Castro. But then Fukushima came, we had the shutdown. Italy was trying to restart in 2010, but then Fukushima came, second referendum, second shutdown. Now, today, it seems that the political mood is changed. For the first time last year, we have 2 motions approved in the parliament, one from the government, one from part of the opposition, both in favor of the reconsideration of nuclear energy. Last year, the Minister of Environment and Energy Security launched a national platform on sustainable nuclear initiative. I was part also of this platform with 7 working groups. Now we are finalizing the report, and Minister Pichetto should go to the Council of Ministers, the last council this year, or one of the first councils at the beginning of 25. The second minister was in favor of that. Minister Urso, that is the Minister of Industry and Made in Italy. They is fully in favor of a reconsideration of a new strategy in nuclear in Italy. And he launched the idea also to set up a new company for nuclear. I will say something on that in a while. There was also a third minister, a Minister of Infrastructure, Minister Salvini, that declared that he was in favor on reconsideration of nuclear in Italy. Latest news in September this year, Confindustria, that is the Italian Association of Manufacturing and Service Companies, is the larger industrial association in Italy. They declared that Italy needs nuclear, industrial sectors in Italy needs nuclear, and they launched a task force on nuclear energy that is working now. More than 50 Italian companies joined the European SMR Industrial Alliance. We are the second largest group of companies in the alliance, second only to France, and is quite amazing because we don't have nuclear reactors in operation. There was also some industrial initiative. For example, EDF Edison, that is the Italian utility owned by EDF, Ansaldo Nucleare, and the Stiller Association in Italy, they signed recently a memorandum of understanding for SMR development, but also for power purchase agreement of nuclear electricity. The last report that was issued was a report by Edison, Ansaldo Nucleare, and Ambrosetti group. The target for SMR in Italy is that if we can target 10-20% of electricity produced by SMR or AMR in Italy, we will create more than 100,000 jobs with a more than 50 billion euros impact on Italy. But more than that, you see here on the lower part of the slide, the first energy scenario analyzed by Edison utility for Italy, comparing a 100 decarbonized electricity sector in Italy, obtained only with renewables. That is the central bar that you see here, where you have more than 60%, almost 70% of electricity produced by renewables and used into the grid, but 27% of electricity produced by renewables that is curtailed. So it is thrown away. If we are going to target a full decarbonized electricity sector in Italy only with renewables, what if we put 8% or 10% of electricity by nuclear and 8% by hydro, 8% by gas with carbon capture and sequestration, and the remaining part with solar and wind? If we have even 10% of nuclear programmable electricity, we may eliminate the curtailment by the renewables, but look at the numbers on the right side. There will be a reduction on system investment and in overcapacity on renewables of about 400 billion euros for Italy. That means we are not asking the citizen to pay for energy storage and grid development and transmission development grid because of renewables. This is a very important economic impact if we include nuclear in an energy strategy for a country. And we are not targeting an ideologic plan of 100% only renewables. We had this December the annual meeting of the Italian Nuclear Association. for the first time, we had a panel with the policymakers, with the member of the parliament of all parties on the same stage. And the discussion was, I would say, quite good because there was not one single totally against nuclear declaration. We had the speech from the Minister of Industry and Made in Italy. He included nuclear in the policy document for Italy for 2030. They declared the interest in deploying SMR or AMR in Italy from 2030 to 2050. The latest news are that in the coming Council of Ministries, in the first councils, there will be a proposal for a new law to set up a nuclear framework for the construction of nuclear in Italy, and the proposal of a new company that should be led by ENEL, the utility, with more than 50% of the shares. Then the largest, one of the largest contribution will be by Ansaldo Energia, Ansaldo Nucleare, and 10% by Leonardo, is another state-controlled company. There are obviously challenges, but also opportunities for Italy, but I don't want to waste too much time on that. I was only to remember that Italy owns a long tradition, I would say, on SMR. University of Rome, they started developing in '86 a small SMR based on pressurized water reactor technology with the loop type, with the fully passive safety system. In the 90s, Ansaldo Nucleare developed an integral PWR. And then in 2000, you see the 10 flags of the 10 countries, the 20 organizations that developed the ARIS concept. And Italy was the largest, let's say, set group of institutions developing that concept. We had a huge experience in experimental activities. For example, in SIET labs in Piacenza, they are the site for the large-scale experimental labs. It is owned by Enea, Enel, Ansaldo, another company, and Politecnico with a smaller 3% share. They are quite famous also in the world for the full-scale testing of components, a passive safety system, integral testing facility. You see the picture on the lower part, the isolation condenser for ESBWR for GE Hitachi, the helical coil steam generators for NuScale, the large testing, integral testing facility for AP1000, and other integral full-scale testing capabilities on the site, up to 10 megawatt electric power available. The last slide is about an exercise that I launched together with Ansaldo last year, at the end of 23 and beginning of 24. I invited the manufacturing companies, the forging companies in Italy that are expert in the nuclear sector. They are more or less 20-25. You see here the logo. And I asked them, how many reactor pressure vessels for SMRs would you be able to manufacture every year? You can download the brochure, but I will leave you the QR code. You can download from the site. We used a scaled IRIS integral PWR reactor pressure vessel for the exercise. Anyway, a large component, more than 13 meters height, more than 3 meters diameter, in carbon steel plus a stainless steel liner. These are the numbers. So imagine that the forging companies are producing forged piece to be moved immediately to the manufacturing companies when they are produced, and the manufacturing companies are assembling and completing the manufacturing process for the SMR integral PWR reactor pressure vessel, Italy would be available after 2 years of transient to produce 8 SMR per year. So 8 SMR reactor pressure vessel per year. That is quite an interesting number. Let me close with the comment on human resources. This is the trend of nuclear engineering graduate students in the 7 Italian universities of the certain consortium that Katrina mentioned. We have the Politecnico di Milano, Turin, then universities of Bologna, of Pisa, of Rome, La Sapienza, and Palermo, and University of Padua, but they are mainly involved on fusion. We had a peak of 250, less than 300 graduated students per year in the 80s when we had 4 nuclear power plants in operation, 1 under construction. Then we had a reduction even before Chernobyl, but after Chernobyl, a steady decline in the numbers. After Fukushima, even we had a minimum of less than 50, but you see the trend in the last 3-4 years. Next year, we may reach the same level of graduated students that we had before Chernobyl accident, without having any nuclear power plants in operation. That is quite amazing. So we have now more or less the same enrollment than pre-Chernobyl. We are targeting the peak in the coming years, and we may say that more or less Italy will graduate, roughly speaking, more than 10% of the European nuclear engineers in the Master of Science student programs. And this is a personal experience that this is my course. I'm teaching Introduction to Nuclear Engineering. It's a 10 credits course in Politecnico. You see the numbers in 2006 and 7, it was 20, 30 students, no more. We have an increase before Fukushima, then we have a decrease in 2012. But after Fukushima, we saw a stable increase with a jump in the last 2 years. Today I have, if I put the number of today, yes, today I have more than 240 students in my course. That is an impressive number of people. I would suggest to close here the seminar. I will anticipate my Merry Christmas, best wishes, and for you, for your families, and I hope really we will have a peaceful 2025. I would say that we may start answering now the question on the chat, if you agree.
Yes, thank you very much, Marco. It was extremely interesting, and I hope our audience was enjoying this information, and I hope that we will have some nice considerations in Ukraine related to SMR development. Speaking about questions, actually, I don't see.
There is one question from
Okay.
Igor Kadenko. It is about, is the University of Pisa involved into SMR activities?
Yeah. Yes, University of Pisa is involved in several of the European Euratom funded projects on SMRs. And I would say that together with the University of Pisa, Politecnico di Milano, and the University of Rome La Sapienza, they are the 3 universities that are more involved on the SMR activities in Italy. Also Politecnico di Torino of Turin, especially on the safety and neutronics topics. So I think that more or less, if not all, several of the Italian universities are involved in the SMR activities. the research activities. Yes.
And related to these questions, the next one is about, do you have a specific course for SMR in Politecnico di Milano?
We don't have specific courses. I'm dealing with the SMR concept during my course. But we had a very interesting experience in the last 2 years. We organized 2 summer schools on SMRs in Politecnico. We invited several experts from IAEA, but also from US, from Japan, from several countries that are involved in the SMR, from Canada on the SMR development. So it is the second time that we organized an SMR school in Italy on the Como Lake, so the venue is quite interesting. We have a 1 week summer school, full time, typically in June, July, and we are thinking about having a new edition in next year. So we may, if you're interested in, we may keep in touch. We may send you the information if we will proceed with an SMR school edition, with the new edition. Anyway, in the last year we have a summer school in Italy, and then a summer school in Romania, in Bucharest. For 2025, there will be a summer school on SMR organized together with our French colleagues. So this is an initiative that is organized also with the ENEN. So there is a ENEN activity on supporting the SMR school in Europe.
Thank you very much. There are no any question in the chat. Maybe someone has a question, please.
Katerina, you're muted.
Yes, as usual. No, I think that we can also accept a few questions from the audience.
Yeah.
If it is nothing in the chat, maybe there is something burning. Raise your hand and ask your question.
This is a lot of information, and we have 15 minutes more.
Okay,
than we
okay.
planned.
Yeah, I was also going to add that to that information about the summer schools. Of course, since NN is also active partner in organization and management of these summer schools mentioned by Marco, and since NN is one of the partners of NURECAB, and we have a task to get Ukraine into good initiatives in Europe. So definitely we are in touch through NN, and it is planned already. So as we discussed already, that maybe some Ukrainian partners will be interested in joining that particular summer school in next year on SMRs. But also, as I mentioned in other workshops which we have had recently, that NN is involved in this Easy SMR project, the big one, the new one, and NN is responsible for organization of 2 summer schools and 4 workshops related particular to SMRs and safety of SMRs. So please just stay tuned, keep in touch with the NURECAB, NN, and check Politecnico di Milano news.
Oh, yes, for sure. On this topic, we are fully available to identify the best way to collaborate with you. So within Euratom project or even with the specific initiatives, we are more than happy to share with you initiatives on this topic.
I would like to say thank you to you from my side and from our Ukrainian audience. It was a very great opportunity to have you today and to get a lot of information. And we are planning to arrange another webinars on these topics, more specific for different topics like fuel cycle, material safety, and so on. And I would like to ask our colleagues to give us feedback. We send you a questionnaire a bit on this topic. And I'd like to ask all of you to turn on your cameras and make a picture of our webinar. That's great. I asked my colleague to make a picture, to make a screenshots.
Yeah, we can do better.
Okay, thank you. Thank you very much to all of you. Thank you very much, Professor Ricotti, for this brilliant information for us. And I would like to wish all of us Happy Merry Christmas and Happy New Year, and that this year will filled with love and peace, first of all. And I hope that next year will bring us the victory of Ukraine and will bring the peace in Europe. Thank you very much.
Thank you to you.
Thank you.
And
Thank you.
if it will be possible
Thank
for
you very
you,
much.
I think that we may also organize a visit, for example, in Italy on the SEAT labs. I think that we may think about different initiatives around this quite interesting SMR topic. So we are fully available to do that. At our best, we will try to work together on this topic. Thank you to you
Thank
for the
you.
invitation.
Thanks a lot.
Thank
Thank
you very
you.
much.
The best. Bye-bye.
Thank you.
Thank
Bye-bye.
you.
Bye.
Thank you. Bye.
Bye.
Merry Christmas.
До свидания.